what do we have? X equals t squared minus and t cubed. Well, we already have the first derivative, so let's go ahead and find the second derivative. So the second derivative, d squared y dx squared, that equals to the derivative with respect to t of the already differentiated function dy dx divided by dx dt, and everything. We already have everything. We have everything from part A, so from the first part of the exercise. So let's see. So dy dx, which for us is the quantity 3t squared over 2t minus 1. So that's the derivative with respect to t of 3t squared over 2t minus 1 divided by dx dt, which is again 2t minus 1. All right? So that's our setup for now. So in this case, we will have to do a quotient rule in the numerator of this derivative. The denominator, just leave it like that. You'll see how in the end, this is going to reduce somewhat nicely. Maybe not the nicest thing in the world, but still. All right. Number one, let's recall what the quotient rule is. So whenever we have a quotient u over v, take the derivative of it. That's u prime v minus v prime u divided by the denominator v quantity squared. That is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, and the whole thing divided by the denominator squared. All right, so let's go ahead and do that. So the derivative of the numerator, which is 6t, and that times the denominator 2t minus 1, minus the derivative of the denominator, which is 2, times the numerator 3t squared. And divide the whole thing by 2t minus 1, quantity squared, but the whole thing is being divided by the quantity 2t minus 1, which is, in this case, the dx dt. All right? Okay, let's simplify this. So let's use the distributive property here. A few times rather, and that's 6 times 2, that's a 12t squared, minus 6t, minus 2 times 3, that's a 6t squared. The whole thing divided by, well, how about in this case, dividing by 2t minus 1 over 1. I'm going to put that placeholder, this 1 right here, and what I'm going to do next is multiply by the reciprocals. I'm going to leave this 2t minus 1 quantity squared times 1 over 2t minus 1 just to the first power. I'm going to just going to put parentheses to it, and then I'm going to put it together with the denominator in the first fraction here. All right. So simplifying terms, that's going to give us 12t squared minus 6t squared. That's a 6t squared minus 6t, and the whole thing divided by 2t minus 1 quantity cubed. And that's the derivative. That's the nicest or the most simplified version of this derivative. Well, so that's the second derivative. So let's use that second derivative to determine the concavity of this function whenever t equals to 2. Again, we're doing all of this around t equals to 2. Okay? So evaluate the second derivative. Evaluate it at t equals to 2. That is, 6 times 2 squared minus 6 times 2, and divided by 2 times 2 minus 1 quantity cubed. And let's see what we get. So 2 squared, that's 4, times 6, that's 24. 24 minus 12, that's a 12. over 2 times 2, which is 4, minus 1, that's 3. 3 cubed, that's 27. Well, since in this case the number, well, actually reduces to 4/9, it doesn't matter. That's a number greater than 0. That's a positive number. This means that at the point where t equals to 2, this function is concave up. Right? It's concave up. Let's see what's next. Yeah. Oh, finding areas. And well, one of the other applications of parametric equations is that view of finding areas, like, and in just the same way that we found areas under curves or functions as described by f of x, by one single function. Well, we can also find areas under curves that are defined in parametric form. Well, so in this case, well, I'm not going to go through all the details of the derivation of the areas. I mean, of the function. However, well, this is how we find it in rectangular form. Just integrate f of x between a and b. That's the area. However, when we have parametric equations, well, this is the y function, and this is the x prime function. So all we have to do is take the derivative of the x function and multiply it with the y function and everything with respect to t. Or, well, the example that I have here for it's in terms of theta, but it's still the same. It's just a dummy variable. The reason we are going to use theta is because we have trigonometric functions, and well, that really doesn't matter that much. All right. And well, these type of problems are going to be pretty straightforward to interpret. I mean, they're going to give you a set of parametric equations, and they're going to give you the limits of integration. That's it. There's really no tricks about it. All right. So in this case, all we need is find the derivative of the x equation, dx dt, well, d theta rather in this case. So the derivative of theta is 1. And the derivative of sine is cosine, right? The y equation just remains the same. All right. So to find the area under the curve, we'll just set up the integral from alpha to beta, in this case, of the integrand, which is g of t, or the y equation, times the derivative of the x equation. And well, the limits of integration are just there. All right. So let's see. Let's set it up. Area equals to the integral from alpha to beta. That's g of t, f prime of t, dt. Well, in our notation for this particular case, it's going to be our x of theta. I mean, no, not the x of the y of theta times x prime of theta. And let's just set it up. So our y of theta, which is, let me highlight actually so you can refer to what it is. Y of theta, it's this part right here, while our cosine, I mean our x prime theta, it's going to be this derivative I found earlier. All right. Let's go ahead and compute this one. So that's the integral from 0 to 2 pi of the quantity 6 times 1 minus cosine times itself 6 times 1 minus cosine d theta. Notice in this case, well, we have a quantity multiplying with itself, so how about we multiply 6 times 6, have that outside of the integral, that's a 36, times the integral from 0 to 2 pi, and that's 1 minus cosine theta quantity squared. And well, it looks like this integral is going to take a good minute to go because, well, you might remember this kind of integrals from almost the beginning of the semester when we look at trigonometric integration. So essentially we are going to integrate a polynomial of trigonometric functions, and we might need some power reduction formulas. I can already see that, of course. Well, so let's see, number one, let's square the binomial first. So that's going to be a 36 times the integral from 0 to 2 pi. That's 1 squared, which is 1, minus 2 times the two terms, 2 cosine theta, plus the squared of the second term. All right? And yes, well, we can already integrate the first two terms. However, that third term, the cosine squared theta, well, we wish we had a factor of sine multiplying with it outside, but that way we can use that as our factor, the tans, the u part, but unfortunately we don't have that, so we will have to use trigonometric identities in this case. So, and in particular, it's the one that I prefer call the power reduction formula, but it's most of the time, I mean, every textbook refers to it as a half angle formula, but I'm going to write those two identities. So number one, the one for cosine squared theta equals 1/2 1 plus sine, or actually cosine, 2 theta. And the other one for sine, the one for sine actually, it's the same, but with a negative in between the 1 and the cosine. Of course, we're going to use the first one, right? Because we want to reduce the power for cosine, and that's going to be the integral from 0 to 2 pi. That's a 1 minus 2 cosine theta plus, okay, 1/2 plus 1/2 cosine theta. So I'm doing two things in one shot right here. So I'm changing the identity here, and at the same time I'm distributing just to save some time. All right, and the next thing would be to reduce or to combine like terms. In this case, the constant terms right here, the 1 with the 1/2. So that's the integral from 0 to 2 pi. And that's 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta d theta. And I think we can integrate the three terms from here. Okay, this is the integral of a constant. Oh, I forgot the 36 here. 36, and yes. Well, let me actually write it in terms of three integrals. I think it would be better so we don't get messed up with all these constant factors. So 36 over 2, that's 18, and 18 times 3, okay, 54. So that's the 54 integral from 0 to 2 pi, and then 36 times 2, that's minus 72 integral from 0 to pi of cosine theta, and 36 over 2, that's 18. And we can already integrate everything. So the integral of the theta, it's just theta, 54 theta, minus 72 sine theta, that's the integral of cosine. And the integral of cosine to theta, careful, that's going to be 18 times 1/2 sine 2 theta. And that evaluated between 0 and 2 pi. All right? And then, well, what's next over here? Just use the fundamental theorem. Evaluate at the upper limit minus evaluated at your lower limit. But check this out. We have a theta here. We have a sine theta and sine 2 theta, values for which evaluated at 0, everything is going to get zeroed out. So that's going to be 54 times 2 pi minus 72 sine. Oh, it's going to be the same for 2 theta as well. That reduces to 9 plus 9 sine times 2 pi, which is going to be 4 pi minus big 0. I mean, that's fine, just evaluate it at 0. But it turns out this is also 0. Sine of 4 theta is 0. Sine of 2 theta is also 0. So we are left with 108 pi. So that's the area under this curve. And well, so what about this this function that we just integrated over? So this is the graph. It's actually called a cycloid. It's a periodic function that just like it's some sort of like the sine or cosine, but like the absolute value of it, if you will. All it does, it bounces up and down, you know, above the x-axis. So, and in this case, our r right here is 6, and we are integrating between 0 and 2 pi r. Well, that's really the area between 2 times pi. That's really 12 pi. All right, that completes at least one cycle of the cycloid. How does that look like on the graphing calculator? Well, so let me go there. So, okay, number 1. All right, let me clear. So what do we have? So it's 6. Well, notice in this case it's going to go with the variable t, because that's the dummy variable for parametric in the graphing calculator. So that's t minus sine t, and 6 times 1 minus cosine t. Okay, let's see. Well, we're not going to be able to see the whole graph because of the window, so we need to make sure that we graph this between 0 and 12 pi. But what's 12 pi? Well, 12 second pi, and graph. Well, for whatever reason, it didn't go through. I don't know why. Oh, I think it's the x, the one I need. 0 and 12 pi. Yeah, we're gonna see the whole thing, one cycle of it. And in the y direction, how about, I'm gonna do 20. Yes, we get to see the whole thing, all right? One cycle. So we're finding the area under this curve. And then what's next? So that was one example. I mean, all the examples are going to look like this. Given the equation, the parametric equations, the limit of integration, and just use the appropriate method of integration, whether this is simply an algebraic one or a trigonometric like this one, a trig substitute. Well, that depends on the function you were given. The last topic for this section, one more. It's finding the arc length. And well, this will be even a lot more simpler than the arc length that we covered somewhat in the middle of the semester. Remember those really, really long problems? We had to do a lot of algebra to simplify that radical expression in the integrand. And well, these ones are going to be a lot simpler, well, especially when it comes to having these trigonometric equations, or functions rather. But of course, you can eventually have some exponentials, some other algebraic that you may need to do some algebra still. So And well, so in this case, well, what do we have? See, here's the formal definition. So essentially, it's the integral between alpha and beta of the square root of dx dt plus dy dt, all both quantity squares, with respect to. Well, just briefly, just to really quickly show where is this sort of coming from. So we can. So you want to find the length between A or alpha and beta. Let's call it alpha and beta. And well, in just the same way that we define the area under the curve, we found the area rectangles partitioned by rectangles and then adding infinitely many of them. In a similar way, we did the derivation of for the formula for arc length, by partitioning this length into infinitely many amounts of lengths that were really, really tiny, and in the end we just took one partition. Let's just call this L, but in this case, to go from this point to that point essentially involves some change in the x direction and some x in the y direction, essentially forming a right triangle. And that horizontal distance for the right triangle, in this case, let's call it delta x, and delta y for the vertical distance. Well, one thing to recall is that this time these two variables x and y are being modified or being changing in the background by this third-party variable called t. So in this case, these two variables delta x and delta y, they both change with respect to t. All right, both change with respect to time. So it requires some time to go from this point to that other point. But of course, that's only one partition of that length that we want to find. However, what if we add infinitely many of those? So for example, we can use the Pythagorean theorem here in the same way that we did before. So L equals to, or rather, let's call this C squared equals A squared plus B squared, and C equals the square root of A squared plus B squared, where C is our big L, and A squared, that's our delta x over delta t, and delta y over delta t, in both cases squared. So that's the length of only one partition. If you want to add infinitely many of those, go to a Riemann sum, and then from the Riemann sum we get to the integral right here, right? I mean, I think it's easier to derive than the other version because everything is with respect to time. The picture, I think it's even clearer than back then, so it's more straightforward, I think. All right, so let's do one example. Find the length of one arc of the cycloid. Let's go back to the cycloid example. X equals 3 sine 3t, y equals 3 cosine 3t. And within the interval 0 to pi. Again, it's just everything is going to be given. There will be nothing cryptic at all. You'll be given everything. All right. So what do we need? We need to find dx dt and dy dt. So dx dt, by mini chain rule, that's going to be 9 sine 3 cosine rather 3t, and dy dt equals to negative 9 sine 3t. All we have to do is set up the integral. So L equals the integral from alpha to beta of the square root of dx dt, quantity squared, plus dy dt, quantity squared, dt. Well, so that's the integral from 0 to 2 pi of the square root of the quantity 9 cosine 3t squared first over here squared plus negative 9 sine 3t squared dt. Let's just simplify the quantity inside of the radical. Well, don't attempt to try and simplify this. A very common mistake I see right here, and you don't want to do this, is to distribute the radical and say, oh, this cancel, that 9, that's a 9 cosine 3t plus, or rather minus 9 sine 3t. No, we cannot distribute the radical over a sum or difference of terms. No, simplify first. You'll see how this is going to look. In fact, it's going to go really, really simple, really nice. So 9 squared, that's 81. That's 81. Cosine squared 3t plus 81, because negative squared becomes positive, sine squared 3t dt. And we can factor out a GCF. In this case, is the number 81. That's 81 cosine squared 3t plus sine squared 3t dt. And well, I think you can recognize an identity here. This one right here, it's the Pythagorean identity, cosine squared plus sine squared, or sine squared plus cosine squared, regardless of the presentation of the order. It's an addition, order doesn't matter. And the identity holds not just for x, which is most likely what you learn initially. I mean, it works for every quantity inside of the parentheses as long as it is the same on both terms. You can have an x cubed, 3t, 5 million, x to the 700, whatever. As long as they are both the same, it holds, and that equals to 1, and 1 times 81, it's just 81, so that's the integral from 0 to 2 pi of the square root of 81, which is 9, and that's equal to 9 times the integral from 0 to 2 pi of dt, and that's 9 times t, or rather 9t, from 0 to 2 pi. And well, 9 times 2 pi minus 0, that's simply 18 pi. All right? So I think it's very, very straightforward problems, right? Well, so, you know what?